Hello, good morning guys. We are almost entering to the end of this topic. Only one more class is there in addition to this class. Then we discuss about the numerical problems that were given in these previous and for this topic. So far in the previous class we discussed about the electrolysis. Electrolysis is a chemical reaction that carried out during the conductance of electricity through an electrolyte. In this electrolytic process, we came to know that certain substances are liberated or discharged at respective electrodes. So, to explain the quantitative relationship between amount of the substance that is deposited or discharged or dissolved at respect to electrodes and the quantity of electricity that was used in the electrolysis was given by Faraday in the form of two laws, namely Faraday's first law and Faraday's second law. Let us discuss one by one. First, Faraday's first law. According to Faraday's first law, in any electrolysis, the weight of the substance that deposited in grams, let W be the weight of substance that deposited in grams, and quantity of electricity that was used in the electrolysis is Q. Then, according to Faraday's first law, the weight of the substance that is deposited at an electrode in an electrolysis is directly proportional to the quantity of electricity that was used in the electrolysis. The weight of the substance that deposited, dissolved or liberated at a given electrode in an electrolysis is directly proportional to the quantity of electricity that used in the electrolysis. Now, W is weight of substance in grams, Q is the quantity of electricity in coulombs. Quantity of electricity is expressed in terms of coulombs, but this quantity is depend upon strength of current and time of electrolysis in seconds. Strength of current is measured in amperes. Strength of current is measured in amperes. So, Q is nothing but C into T or I into T. Sometimes the strength is designated with capital I and some books it was designated as C, whatever it may be, it makes no difference, IT or CT. So, this will be the quantity of electricity Q. Therefore, W is directly proportional to I into T, where I is the strength of current in amperes and T is the duration of electrolysis in seconds. Or we can write it as W is equal to EIT. This small e is a constant. It is called as electrochemical equivalent. This constant is also called as E is equal constant. and it is known as electrochemical equivalent. Electrochemical equivalent. The small e is a constant, it is called as electrochemical equivalent. If 1 ampere strength of current is passed for 1 second, I is equal to 1 and T is equal to 1. In such case, I into T is equal to 1 and it will be equal to 1 coulomb. If 1 ampere strength of current was passed for or used for 1 second, the total quantity of electricity will be equal to 1 coulomb. So, if 1 coulomb of electricity was passed, I is equal to 1 and C is equal to 1. So, the total will be equal to 1. In such case, W is equal to small e. Now, the small e electrochemical equivalent can be defined as the quantity of any substance, whatever it may be, that liberated or dissolved or discharged in an electrolysis at an electrode, that weight that liberated for 1 coulomb of electricity is equal to electrochemical equivalent of that substance. For example, if x grams of copper was deposited for 1 coulomb of electricity, x is the electrochemical equivalent of copper. If x grams of silver is deposited with 1 coulomb of electricity in an electrolysis, that x is the electrochemical equivalent weight of silver. Just like an atomic weight, for each and every atom, this electrochemical equivalent is a constant. It is constant. It is one of the characteristic property of a substance. Just like atomic weight, we know atomic weight of any element is fixed. Likewise, this electrochemical equivalent for any element is a fixed value. This is the weight in grams that is deposited for 1 coulomb of electricity. Its unit is gram per coulomb. Now, from Faraday's first law, we came to know that electrochemical equivalent weight is the weight of the substance in grams that is deposited for 1 coulomb of electricity. Now, in second law, we came to know that weight of the substances deposited are in the ratio of their equivalent weight. Why they are in the ratio of their equivalent weights? And what is the equivalent weight? And why it was related in that ratio? Let us discuss or clarify these doubts. Now, for that purpose, let us see how an atom is deposited at an electrode. For example, when if you take silver atom, in silver nitrate solution, silver is in the form of Ag plus ions. Whereas in electrolysis, at silver, at cathode, it was depositing as Ag. It means in electrolysis, Ag plus ion is converted as Ag atom. It is possible only when it accepts 1 electron. So, Ag plus ion by accepting 1 electron deposited as Ag atom. If you want to deposit 1 mole of Ag, each Ag atom requires 1 electron. So, you require 1 mole of electrons. So, to deposit 1 mole of Ag, you require 1 mole of electrons. Now, you know, even atomic structure itself, you know, came to know that charge of an electron charge of a single electron is 1.603 into 10 to the power minus 19 coulombs. Now, to deposit 1 mole of silver you require 1 mole of electrons. Therefore, number of electrons in 1 mole. 1 more electrons means nothing but 6.023 Avogadro number into 10 to the power 23 electrons. Now, the total charge of 1 mole of electrons is the product of these two. 1.603 into 10 to the power minus 19 into 6.023 into 10 to the power 10 to the power 23. It will be 96,500 coulombs approximately. 484 something like that. It is approximately 96,500 coulombs, and this quantity is known as 1 Faraday. This quantity is known as 1 Faraday. So, with 1 Faraday of electricity or with 1 mole of electrons, 1 mole of Ag is going to be deposited. What is in the case of copper? Copper, in copper sulfate solution, Cu plus 2, copper is in the form of Cu plus 2 and it is deposited as Cu. Now, Cu plus 2 ion deposited as Cu or converted as Cu only when it accepts 2 electrons. So, this is the difference. Here Ag plus requires only 1 electron to deposit as Ag, whereas Cu plus 2 required 2 electrons. That is double the number of atoms. So, if you want to deposit 1 mole of copper, you require 2 moles of electrons. That means 2 Faradays of electricity is required to deposit 1 mole of copper. Now, here with these both electrolytic cells, suppose if I pass only 1 Faraday of electricity, what happens? If I use 1 Faraday of electricity, that is 96,500 coulombs, or 1 mole of electrons are used in the electrolysis, then 1 mole of Ag is deposited, but half mole of silver is depositing. 1 mole of silver is depositing and half mole of copper is going to deposit. Here comes the equivalent weight. Equivalent weight is nothing but atomic weight by its charge. Here in silver, charge is 1. Therefore, atomic weight by 1 is its equivalent weight. In copper, charge is 2. So, equivalent weight is 1 by 2. In aluminum, charge is plus 3. So, equivalent weight is atomic weight by 3. That means the amount of the substances that deposited here, 1 mole of silver is equal to 1 gram equivalent weight of silver. Half mole of copper is equal to 1 gram equivalent weight of copper. If there is aluminum, 1 mole of aluminum, 1 by 3 mole of aluminum is equal to 1 gram equivalent weight of Al. Or if you take stannic chloride, Sn plus 4 ions are there. So, only 1/4 mole is depositing. That 1/4 mole is the equivalent weight of stannic ions. So, that is why they are in the ratio of their equivalent weights. So, the doubt that arises for us is why the amount of the substances deposited are in the ratio of their equivalent weight. Equivalent weight of an element will depend upon the number of electrons that required to deposit that atom or 1 mole of atom. So, basing on the number of electrons required by the ion, the quantity of electricity will depends. So, if same quantity of electricity was used, that is why the elements are deposited in the ratio of their equivalent weights. So, from this it is evident for any substance in general, the weight of the substance that deposited for 1 coulomb of electricity is nothing but its equivalent weight. This is the final conclusion from the Faraday's second law. That is, the weight of the substance that deposited for 1 Faraday of electricity is nothing but the gram equivalent weight of that substance. So, gram equivalent weight of substance is nothing but weight of substance deposited for 1 Faraday or 96,500 coulombs. Equivalent weight, let equivalent weight is denoted with capital E. That capital E is nothing but m by z, where m is atomic weight and z is valency or charge. Valency or charge. Equivalent weight is nothing but atomic weight by valency, m by z. So, equivalent weight of the substance is nothing but weight of the substance in grams that going to deposit with 96,500 coulombs or 1 Faraday of electricity. If 96,500 coulombs deposits 1 gram equivalent weight of substance, 1 coulomb will deposit how much? That is E by F. This is the amount of substance that deposited for 1 coulomb is E by F. Now, come to the first law. According to first law, W is equal to E I T, weight of the substance in grams that deposited in an electrolysis is equal to E I T, where E is the electrochemical equivalent, I is the charge of, that is strength of current in amperes, whereas T is the time of electrolysis in seconds. Now, but this electrochemical equivalent is nothing but the weight of the substance that deposited for 1 coulomb of electricity. Now, we came to know that weight of the substance that deposited 1 coulomb of electricity is equal to E by F, and it is again equal to small e. So, instead of small e, you can substitute E by F, then W is equal to E I T by F. But E is equal to m by z. If you replace m with z, then it will be m I T by z f. This is the final relation between weight, atomic weight, strength of current, time flow, valency and Faraday. So, here W is the weight of the substance in grams, m is the atomic weight of that element which is going to deposit in an electrolysis, I is the strength of current in amperes, T is the duration of electrolysis. If quantity of current was given, then instead of IT you will write Q also here in coulombs, then Z is the valency and F is the Faraday. So, if you know any out of here, how many parameters are there? 6 parameters are there. If you know 5 parameters, you can calculate 6th parameter. This formula is most important formula derived from Faraday's 2 laws, first law and second law. On computing Faraday's first law and second law, finally we get this formula. With the help of this formula, we are going to do so many numerical problems relating the Faraday's law. Now, let us discuss Faraday's second law. So, in Faraday's first law, we came to know that weight of the relationship between weight of the substance and quantity of electricity that was deposited at an electrode. In that first law, one thing that should be remember and recollect, which we are going to use in the second law, that is electrochemical equivalent. Electrochemical equivalent is the weight of substance that deposited for 1 coulomb of electricity. Weight of the substance that deposited for 1 coulomb of electricity is known as electrochemical equivalent. Weight of the substance that deposited for 1 coulomb of electricity is known as electrochemical equivalent. This value we are going to use it in the second law also. According to Faraday's second law, what he said that when same quantity of electricity was passed through different electrolytic cells, the weight of the substance set that deposited at respective electrodes are in the ratio of their equivalent weights. When same quantity of electricity was passed through different electrolytic cell, the weight of the substances that deposited at respective electrodes are in the ratio of their gram equivalent weights. This is Faraday's second law. Let us illustrate this. Now I am going to take an electrolytic cell which contains silver nitrate solution with silver or platinum electrodes, and I am taking another pot which is having acidulated water with platinum electrodes, and another vessel I am taking, here I am taking copper sulphate solution with copper electrodes. Now I am connecting all these three electrolytic cells in a series, then I connected it to a battery. So if I make the setup like this, same quantity of electricity will pass through these electrolytic cells. Now let us take this one as acidulated water with platinum electrodes, AgNO3 with Ag electrodes, CuSO4 solution with copper electrodes. Now here in this cathode hydrogen gas is liberated, here in this cathode silver is deposited, here in this cathode copper is going to deposit. I am not discussing about the substances that liberated at anode, because anode also follows the same law. That means the weight of all these substances, let the weight of hydrogen that liberated is W1, and weight of silver that liberated is W2, and weight of copper that liberated is W3. Then according to Faraday's first law, W1 is to W2 is to W3 is equal to E1 is to E2 is to E3, where E1, E2, E3 are equivalent weights of hydrogen, silver and copper respectively. Hydrogen equivalent weight is 1.008, silver equivalent weight is 107.9, whereas copper equivalent weight is 31.8, because its molecular weight is 65.3 by 2 is 31.8. So the weight of the silver, copper and hydrogen that liberated are in the ratio of their equivalent weight. This is Faraday's second law. What is Faraday's second law? When same quantity of electricity is passed through different electrolytic cells, the weight of the substance deposited at respective electrodes is in the ratio of their equivalent weights. Not only for different electrolytes, the same principle is applied for the substance that deposited at cathode and anode. For example, if you electrolyze acidulated water, at cathode you will liberate hydrogen, and at anode you will get oxygen, and those weights are also in the ratio of their equivalent weights. That is, hydrogen is to weight of hydrogen is to weight of oxygen will be 1:8. The ratio of the substance deposited at cathode and anode will also in the same ratio. This is Faraday's second law. In Faraday's first law, what he said? The weight of the substance in grams that deposited at an electrode is directly proportional to the quantity of electricity that passed through the electrolyte. In the second law, he says that when same quantity of electricity is passed through different electrolytic cells, the weight of the substance that deposited at respect to electrodes are in the ratio of their equivalent weights. I further illustrate the second law to get the relationship between weight of the substances and other parameters that involved in the electrolysis, because that formula is most important to derive the relationship between those parameters that are involved in the electrolytic process. In the most of the numerical problems, we need that formula. Let us discuss that formula.